And here you go. Okay, so what I want to do is talk about image formation. So we'll talk about the pinhole camera model. Then two kinds of projection means projection through this pinhole camera model for us, and we will talk about two types: uh, the strong perspective or just perspective, and the weak perspective. So these two things, and then we will talk about some camera basics, depending on how much time we have got remaining. So let's start about this pinhole perspective first. Yeah. So this is what I want to talk about. And now I can use the pen. Okay, so first let's talk about the pinhole camera. So this is an idea that has been around for many years, and it was accidentally discovered. I think the story goes that some tent in a desert, somebody observed that a hole in one of the sides of the tent created an image of the outside world on the other side of the tent. Okay, so something like that. I don't know exactly what, but anyway. So the point is that this idea has been around for a long time, and we'll take a look at what that idea is. So suppose here you have a screen, okay, and here is your object. Okay, and you have nothing in between. So here's your object, here's your screen, and there's daylight, let's suppose. What's going to happen is that the light rays coming from, or maybe, even maybe this is just your, instead of object, you can take a light source. Okay, so instead of this, you can think of it as a light source. So then, in that case, what will happen is that, the rays coming from any part of this light source are going to fall all over the screen. Okay, and so you will simply have a bright screen here. Okay, now if you want actually the image of an object, so instead of a light source, there could be an object, and then what is happening is simply the light coming from any part of that object is falling all over the screen. Again, you're not getting any information from the screen. So the thing to do is to put a barrier between the light source and the screen so that all this extra light is blocked out. Okay, and so that is the idea of a pinhole. So what is done is that you put some barrier with a small hole between the object and the screen so that the light rays coming from the object, there's only, instead of all these rays falling all over the screen, there is only hopefully like one or few rays that pass through this pinhole and reach the image screen. Okay, and so on for all parts of that image, for all parts of the object. Okay. This is also the reason, from this ray diagram, you can see also the reason why the image is going to appear upside down. Okay, so light rays from the top of the object reach, say, here, and light rays from the bottom of the object will reach a point up here. And so the entire object is going to appear upside down on the image screen. And this is the idea of a pinhole, and hence of a pinhole camera. Okay, so this is what a pinhole camera model means. And if you want to see a better picture, here we have it. So now instead of a barrier like that, we are thinking of a box. This is probably something you have seen in school. Right, this pinhole perspective is probably what you have seen in some physics lab in school, that you have a box here and then your object or a candle on the other side, and the candle appears reversed on the screen behind the pinhole. Right? So this is called as the pinhole perspective. Okay. Now there are a few simple observations that you can make from this, and this is also was probably part of your physics class. One of the things that are obvious is that farther objects will appear smaller, right? So we can sort of look here. So the object B is farther away from the object C. Okay, if you look at the distance between the pinhole O here, okay, if you look at this distance and this distance, well, B is farther away from O than C. And then if you look at their what you get on the image plane, then you will see that the object that was farther away is appearing small here. Okay. In this case, actually, the design has been done in such a way so that C and B appear to be of the same sizes. So I don't know if you have seen this. What is it called? These kind of images that seem to fool you. Okay, some person appearing extremely tall and another person appearing extremely short next to that same person. Okay, so these kind of images are taken usually in a room or a background with pattern on it. Okay, and this is exactly the kind of thing that is done. Okay, so you can have a tall person stand here and a short person stand here, but then if the distance is really far, they will probably appear of the same height or in the image. Okay, so well, this is a very basic principle of pinhole perspective. Then lines project to lines, and that is very important for us when we are studying image formation. Okay, that lines will go to straight lines, go to straight lines. Okay, so and projections of lines that of parallel lines lying in a plane phi appear to converge at a point. So this thing I will discuss a bit, but the first 2 points I think you can convince yourself, or you can use Euclidean geometry, because well, if you look at this image, or even here, okay, so suppose I call this as O, this as A, and this point as B. Okay, and so here I call the image of capital B as small b, image of capital A as small a. Okay, then the triangles OAB and capital OAB are similar. Okay, so using this similarity and fixing some distance between these, okay, you can easily convince yourself of properties 1 and 2. Okay. So property 3 is something that we can talk about a little. And I just want to mention the fourth one also in the same vein, that vanishing points of coplanar sets of lines are collinear and form the vanishing line of the plane. Okay, so these are 2 things that we will discuss a bit. So what does it mean? One thing that we are going to do in this entire discussion is, so here you have the actual image plane, okay, and this is your object. Now notice that, so suppose D is the distance between the image plane and this screen that contains the pinhole, okay. So later we will also call this as the camera plane. That's for later. Right now it is the pinhole plane, okay. So suppose this distance is D, okay. Now it's not difficult to imagine that, so the rays coming down from A, okay, if you sort of put a screen here in between at the same distance, okay, so if you put a screen here at this same distance, and if there was a way of capturing just these rays, okay, then you would get this, the image of the object here, and that would not be inverted. Okay, if there was a way of capturing these rays, okay, then this same thing would be here with the object not inverted. Okay, so oftentimes it is, you know, easier to talk about this plane rather than the image plane itself. So what is the difference between the image plane and this? This is called as the virtual image, or this plane is called the virtual plane, virtual image plane. So simply virtual plane. What is the difference between the image plane and virtual image plane? Not much. The main difference is that The image plane is the actual screen, okay, and the image appears inverted on it. Whereas the virtual image plane is just a convenient way to describe the image plane. Okay, so the distance is the same, only this is between the object and the pinhole, and the image is not inverted. Okay, there is no other difference between the image plane and virtual image plane. And that is why it is sometimes convenient to talk or work with this rather than this. Okay, so that is just something to keep in mind. We might use this virtual image plane from time to time. Okay. Because you will see it's convenient to talk, especially when this object is really far away. Okay, it is convenient to use this virtual plane. Okay. So as I said, let's talk about why projections of parallel lines lying in a plane phi appear to converge at a point, which we will say is a point on the horizon. Okay, so let's look at this image. So here, what is happening is that, so this thing here is the virtual image screen. Okay, here is my pinhole, and the actual image screen is somewhere here. Okay, somewhere behind here. Okay. This is the virtual screen or the virtual image plane. Yeah, so here is the pinhole, and on this side is the real world. Okay, and this is the virtual screen. Correct. So what so the point that I'm trying to make here is that projections of parallel lines lying in a plane will converge to a point. So what do I mean by projection? Projection means, so here is a line L1, okay, and here is a line L2, and for practical purposes you can think of these as, you know, railway lines, railway tracks, okay, in the real world. That sort of makes imagining this easier. Okay, so suppose these are two parallel lines lying in a plane phi. Okay, here is my plane. And for convenience, I have taken this plane like this, but this plane could be even tilted or whatever. Okay, for convenience, right now it is, we are thinking of it lying, you know, horizontally like this. Okay, so suppose I pick up a point here on L1 and a point on L2. I want to see what this point maps to in the virtual image plane. Okay, so for that, what do? We look at the light ray going from the point on L1 to the pinhole. Wherever that intersects this virtual plane, say this point, then that's where the projection will be. Okay, by projection, I'm simply meaning, I mean, not some, you know, linear transformation right now. By projection, I simply mean the point where this ray meets the image screen. And the ray coming from this point on L2 meets the virtual image screen here. Okay, so now you can look at the point where this line sort of meets the screen. Okay, so that's this point. And this line L2 meets the screen at this point. Okay, so these are the two starting points, and these are some other 2 points here. Okay, so suppose you are traveling in this direction on L1 and traveling in this direction on L2. Then on the screen, you are traveling in this direction and in this direction. Is this much clear?
Yes, ma'am. I guess if you can tell us that example, that whenever we take a picture of a line or something or a road from a particular point, then they meet in the
Exactly.
environment.
That is exactly what I'm trying to convey here.
Okay.
Okay. And why does that happen? That's what I'm trying to say. Okay. So that happens because, well, this, as you keep on going farther and farther away, okay, you will keep on getting points on these. One is this line that corresponds to L1. Sorry, I lost that highlighter again. So one is this line which corresponds to the point images from L1, and the other is this line which corresponds to images from L2. Right? So what is going to happen is, as you go farther and farther away here, okay, these two lines will converge to some point here. And that point is not necessarily in the image. Okay, this is a virtual screen. You can imagine it to be huge, but your actual image on the other side could be small, and you may not even see this vanishing point. Okay, but the point is that these lines will not be parallel in the image. Okay, and this is exactly what happens when you take images of railway tracks. If you have seen the picture of a railway track anytime, you will see that in the image, they don't appear parallel. Okay, and that's exactly for this reason. Okay, these lines will appear to meet at some point, which may or may not be in the actual image. And that point is called as the vanishing point. Okay. Now, if you take any other pair of parallel lines in the same plane, so here is another pair of parallel lines, then you can show this using Euclidean geometry again, that these two, if you look at their images in here, okay, they will also have a vanishing point. And the set of all such vanishing points, if you're fixing this plane phi, and you're taking any two parallel lines anywhere, and you look at the set of all vanishing points of these parallel lines, they will fall on a line which is called as the vanishing line. Or in fact, that is what we mean, or that is what corresponds to the horizon. Okay, and in fact, it can be shown that any two such vanishing points coming from lines in the same plane will be collinear. Not two, any three. So they will be collinear, which means you will have a vanishing line here, which is called the horizon, or which corresponds to the horizon in the image plane.
So does the horizon line depend on the phi that we take, the phi plane?
Yes, the horizon line in the image depends on what plane you're talking about.
Okay, right. So we
This
could
is
have
with
taken,
respect to a fixed plane, yes.
okay, we could have taken something at an angle, like the dotted lines you showed.
Yes.
And so the horizon will be different?
Yes.
Okay.
This is all with respect to a fixed plane.
Okay, okay.
Okay.
Ma'am, also, but if we take a plane at an angle, won't the vanishing point, won't it have infinite height? Like if you take something at an angle, they won't appear to converge unless it goes to infinity, right?
So I'm not saying that this point will be in your image.
Okay.
As far as theory goes, this screen is infinite, no?
Okay, right. Okay.
Yeah. So but your image is finite. You may not see this vanishing point appearing on your image.
Okay. Okay.
Okay. So, but for language, see, what we are trying to do here is develop language. For language reasons, this point where these parallel lines will appear to meet in your virtual screen, it will be called as the vanishing point, so that you know what this concept is.
Okay. So the whole convergence is happening because of the perspective that we are watching from the pinhole.
Exactly,
right?
exactly. Yeah, because these light rays are going through this pinhole.
Okay. Now it makes
this
sense.
Is all similarity of, you can prove this using just similarity of triangles.
Yes, got it, ma'am.
Okay. So because we will be using these words vanishing point and horizon later, so that is why this idea should be clear. That's all. Okay. So that is what we mean by this statement here, number 3, that projections of parallel lines lying in a plane phi appear to converge at a point, and the collection of all these points will be called the horizon. The point is that you will have parallel lines appearing as converging in the image. Okay. And this second point, this fourth point is also what I said. If you do this vanishing points of coplanar sets of parallel lines, I should say here. Okay, I should sets of parallel lines are collinear. This can also be shown and form the vanishing line in this plane. This thing here, horizon. Okay, so these are just some observations that can be proven using Euclidean geometry, but we just need to be aware of this because these are the basic things that come in with a pinhole perspective. Okay. And there are other things also that you can prove with Euclidean geometry, but for convenience of language as well as the later transformations that we want to study, it is useful to use reference frames and coordinates. Okay, so that is what I'm going to do now, is going to introduce reference frames for the pinhole, the image plane, and the object plane. Okay, so let me move on. So what we do is we associate a coordinate system, let's call it OIJK, to the pinhole camera with the origin O. Okay, so what we will do here is, so let's go to this or even the earlier image. Okay, so here we will have the camera plane. This pinhole itself will be the origin of this plane. Okay, then the object we will assume, this is real world. Okay, the object is in the real world, and this will be the real world coordinates. Real world coordinates. This is the camera plane coordinates with origin at the pinhole, which means I'm going to take directions I and, so this is on the plane, not in the direction of the ray. Okay. So I and J, okay, that's the camera plane, and here is the image plane. Okay, so for the image plane also I want image coordinates. Now this is the camera plane, is a plane 2-dimensional, image coordinates also plane 2-dimensional. So there is no question about points here, they will be 2-dimensional. Okay, there is no question about points here, they will be 3-dimensional. The points in the camera plane will be 2-dimensional, but when we want to talk about distance between the camera plane and the object, we will talk about K. Okay, so the third dimension here, I don't know how to draw this so that it will be clear. Okay, this third dimension here, K. Okay, so we will say that the object lies on the principal axis, which is in the direction K. Okay, so that is how we do it. Let me make it, I mean, it's written down properly here. Oh, I have another image here. Yeah, so we associate coordinate system OIJK to the pinhole camera like this. Okay, so this is what I was trying to draw. This is your camera plane. And the origin coincides with the pinhole. The vectors I and J form a basis for this plane. And the image plane, which I'm calling phi, lies at some distance in the direction of the vector K. Okay, so that is the assumption, or that is the setting. So pi is located at as a distance, let's say D, along this vector K. Okay. This along the vector K, this line is called as the optical axis. So this is your optical axis. And the point at which this optical axis meets the image plane here, the point where this optical axis meets this image plane is called as the or is taken as the origin of the coordinate system in the image plane. Okay, so I'll call that point C. Is this much clear? So this is the setting on the between the camera plane and the image plane. And of course, there are real world points. Okay. So we will always use uppercase letters to denote real world points and lowercase letters to denote the image points. That will be our notation. Okay. So suppose P, X, Y, Z is a scene point, which means a real world point, which is projected through this camera to a point small p, small x, y, z. Okay. And so here is the sort of image or picture of that thing. So here you have a scene point, capital P. Here is your pinhole, also the origin of this coordinate system. And the light ray coming from P is passing and meeting the image plane at small p here. Okay. the optical axis is cutting the point, the plane pi at the point C. So this is your image center. Okay. Let me make it clear that when I say image center for now, I'm just saying the origin of the image plane. This has got nothing to do right now with, so this is your picture, I don't know, 1086 by 2000 pixels, suppose. This center has got nothing to do with this center right now. Okay. So let me just make that clear. These two things are not related right now. We'll see later how they are related. Okay, so just that clarification. So here is this the point where the optical axis meets the image plane. Now the thing to see is that this, of course, capital P, O, and small p are collinear. Okay, and if this distance I'm calling as d, okay, then because these are collinear, you can say that vector OP is equal to is a scalar multiple of vector capital OP. Right? Now, presumably, this distance is going to be smaller than this distance. The distance between camera and the image plane is going to be smaller than this one. So I'm going to put lambda on the other side. So I'm going to say O small p bar is some lambda times O capital P bar, because they are collinear. Okay. And now, because these are written in vector coordinates, well, what is OP bar? OP bar is the vector xyz. Okay, and O capital P bar is the vector capital X, capital Y, capital Z. Okay, now the point to note here is that don't get lost with all the coordinate systems. This xyz is with respect to these ijk for now. Okay, so we have kept this fixed. Everything is going on with respect to this ijk for now. And I've just written the coordinates like this. Okay, so this is happening all with respect to this one coordinate system for now. And with respect to this, we have this equation. Okay, and so now if you say that OP bar is lambda times capital OP bar, then that translates to, in terms of the coordinates, it translates to small x is lambda times capital X, small y is lambda times capital Y, small z is lambda times capital Z. Fine. So now what you can do is collect these together, write them nicely as lambda being equal to these ratios. Well, why did I replace it by small d? Because, well, this distance is exactly what the z is going to be, because that is in the direction of the third component. Right? So this z for all points in the image plane is going to be d. Correct? Because all points in the image plane lie at this distance d, and that is the direction of k. So I can replace that small z by d. And so now what I can do is I can write small x equals d over z capital X. And I can write small y equals d over z capital Y. Okay, so I've gotten rid of this, not required. And the same thing I've just rewritten in this way. So small x is d times this ratio, and small y is d times this ratio, capital Y by capital Z. Okay, so we got this set of equations, which is called as the strong perspective equations. Very straightforward, right? This is just following from this collinearity. The only thing you have to keep in mind is that this is going on with respect to this coordinate system, and then you can keep track of stuff. Okay, everything clear up to here? Are there any questions? Okay, so if there are no questions, let's move on to what is the weak perspective model. So, well, most commonly, this is the situation that we will be in. Okay, most commonly, we will be dealing with the strong perspective equations, or sometimes this is just called perspective equations. You don't even say strong. These are the basic perspective equations. Okay, but sometimes what can happen is that there are some situations when this distance d is very small. Of course, I mean, in real life, this distance d is very small because this entire setting is within your camera. This image plane is going to be nothing but your sensor. This is nothing but the center of the camera lens. So this distance is really small in, if you're thinking about taking pictures with a camera. And this distance can be huge. For example, look, think of a situation, you have those sports events and there are cameramen sitting, really far from the field. Okay. So in that kind of situation, you can imagine that this distance is negligible if you consider the distance of the camera from the place where the game is happening. Okay. So in that kind of situation, you can make one more small assumption. What is that small assumption? That the scene of which the image is being taken has a small relief. Okay, what does it mean, relief? Relief means, suppose that all the scene elements, okay, can be thought of as lying between two planes which are parallel to the camera plane. Okay, if all these scene elements are lying between two parallel planes, okay, which are also not too far from each other. Okay, this distance L, let's say, between these two parallel planes is not too much. This distance is called the scene relief. Okay, scene relief means how much is this distance, or how. So in like, if you have ever visited places and you have seen carvings and all, it's called a relief, right? So there is a stone or something, and on that there is some carving. So this is called as a relief. This is exactly because all the elements lie between such two planes. Okay. So in general, the sort of scenario that I was talking about earlier, that you have a cameraman sitting in the stands, and there's a game going on, and or even sometimes on top of the stands. In such a situation, you can sort of imagine that this distance is so huge, and comparatively this distance is small. Okay, all scene elements lie within a small distance of each other, okay, compared to this distance. Then in that case, what one can do is, instead of having such a diagram or such a description of the situation, there is a sort of simpler description. Okay, that simpler description is called the weak perspective model. So this is not used always, and this is sort of a coarser approximation to this whole imaging process, but it is useful in some situations, and it's very simple. So in this case, what one does is, one thinks of, so here again you have your camera plane, okay, here you have your image plane, and here is the scene point. Okay, so now, because the scene relief is small, you can sort of think that all the scene elements lie in a plane. Okay, again, this is a huge approximation, but for mathematical purposes, because the distance anyway between these two is going to be small, you can think that all of them lie in sort of some parallel plane. Okay, what we want to really say is that, in that earlier picture where all scene elements lie at some distance, let's say capital Z0, what I want to say is, all these for all the coordinates coming from all these points, Z0 is fixed. That's what I want to say. That is the whole reason why we want to say scene relief is small, because I want to sort of, for every point in the scene, I want to say the Z coordinate is the same. Okay, and that is the mathematical approximation you can do if all these things are true, that if the scene relief is small compared to the distance from the camera. Okay, so with this small approximation, your earlier equations simplify to so now what has happened is, this z is no longer changing along with the points. This z is fixed. Okay, this Z some Z naught, right? So now what I've done is I've just collected the D over Z naught separately and written it as M. And so now these two equations, look like this. Okay, so these are called as weak perspective equations. That's all. Okay, so yeah, so this is also language that you will see in this context. That is, this weak perspective is sometimes called orthography. Orthography means what? So you know, in engineering and all, they use this word. Orthography simply means, so if you have say a 3D object in space and you're viewing it from the top, let's say, then how is it going to look in the XY plane? Or if you view it from the sides, then how is the projection going to look in the corresponding whatever ZX or ZY planes? Okay, so these are called as orthographies. Okay, and because this weak perspective sort of, you know, I mean, you can think of it as an orthography, right? So your scene relief, scene is here, and your virtual image plane is here, and you're sort of thinking how, if the ray of light is coming from this side, the objects are going to be projected on this plane. You know, just a way of saying that, you know, this weak perspective is like your orthography that you might have seen in engineering drawing. So this is just words that you will see. So I'm mentioning them all. Okay. Usually this is unrealistic. We don't talk about orthography or weak perspective in the usual imaging process. In the usual process, we usually just take this. These are our perspective equations. Okay. But you know, you will, if you read about this stuff, you will read about weak perspective, and then you will say, oh, we never talked about this in class. So I just mentioned this whole business. There are the basic geometric properties, okay, which come from a pinhole camera model. And this pinhole camera model can be used to describe the mathematical modeling process, which is the perspective projection. Okay, in strong perspective, well, angles are not preserved, projections of parallel lines meet in a point. So we have seen this. Okay, in the weak perspective model, because you can think of it as an orthography, the angles are preserved and projections of parallel lines are almost parallel. Okay, so this is sort of an image that attempts to explain this. Okay, so here you have your usual perspective, usual model. Okay. And now if the distance from camera goes on increasing, okay, then you can sort of think of it as becoming like this. Okay, this object is going farther and farther away from the camera. Then the mathematical model can be made weaker and be thought of as a weak perspective, or simply this projection or orthography. That is what the whole business I was talking about is. Okay, so now we have got the basic mathematical model for the imaging process or the perspective model. Okay, so now what I want to talk about is camera with lenses. So as you know, we don't use pinholes, we use cameras which have lenses in them. So the first question is, why should we use lenses? Okay, why should we use lenses instead of just having a pinhole? It would have been much easy in manufacturing if, you know, even your handheld device had just a hole and then and the shutter, right? No lens in between, then the cost would come so down. If you have a lens, okay, it collects light and then it focuses it. Okay, so the rays are converging. Okay, so then you can afford to have a small distance between the lens and the screen. That is right. Okay, so that is one reason.
Ma'am, maybe to gather more light.
To gather more light. Yes, exactly. So that is one more reason why we should have lenses, because lenses, because of, you know, again, this, what happened? Yeah, this shape, they gather more light. Okay, so yes, you want lenses so that they can gather more light.
Ma'am, but what would be the effect of that? Like what actually improves when we are gathering more light that we don't get to the pinhole?
Yes. So what happens is, when you have a pinhole, it doesn't allow light. That's what I've written here. Pinholes will not allow much light, which means the image itself will be dark. Okay, you won't get a bright image. When more light is collected, first of all, more part of the scene becomes visible, and then the image also becomes brighter. So these are two things that happen when more light is collected.
And also,
Okay.
ma'am, there is something called wide angle. So if we wish to capture more area,
Yes,
then
yes.
the
So
lens
wide
is
angle
required.
lenses will capture even more wider images. Okay,
Yeah.
even more than the simple lens will capture. Okay, but definitely what I want to say is that a pinhole, whatever light it captures, is much less to make a bright image. Okay, the image will look exactly like what you have seen in your physics lab. And do you want your photographs to be like that? No, right? So, so that's one thing, that you cannot collect a lot of light with a pinhole. It doesn't allow much light. And the second thing is, your image doesn't become bright. That's one reason why you want lenses. The other thing is that if you try to solve your problem with just allowing a larger pinhole, okay, you want more light, okay, take a larger pinhole. Then what's going to happen is the light coming from a point P, it's not going to be just one ray, okay, or a thin ray, or maybe even with your, humans, whatever you can make a pinhole, there will be lots of rays coming through it. Okay, for our measurement purposes, it's it's one ray. But anyway, if you make a larger pinhole, you will allow lots of light rays. And so this one point will actually create all this on your image. And imagine what happens when all the points on your object create these kind of uh, uh, create these many artifacts on your image. It's going to be a very blurred image, right?
Yes.
So a small pinhole won't allow enough light, and a bigger pinhole will blur the image. And both these problems are solved when lenses are used, because lenses will collect more light and they
Could
will
you just
focus.
could you just explain the problem with bigger pinholes? Why would the image be blurred?
Yeah, so the problem with bigger pinholes, as as is in the diagram here. So this is my bigger pinhole, right? And now there is a point P on the object. The light rays coming from this point P there will be, instead of your ideal situation where from point P you have just a single ray coming to your image screen. That is your ideal situation, right? What is going to happen now is that there more light is going to be allowed from the same point. This is going to happen for every point in the object. Now, if we just fixate on one point and look at this, that one point projects to all this area on the image screen. Whereas here in the ideal situation, the point P projects to a point on the image screen. So points correspond to points in the ideal situation. But when you have a bigger pinhole, points will correspond to, I don't know, some band here, an area. Okay? Actually,
Yeah, got
circular.
it.
This is circular, so it is going to be a huge dot here. One point here is going to be like a huge dot here. And this is going to happen for every point in the object. So for every point, you're going to have like these dots, huge dots. Okay. And now if you actually had some shape from which you want to make sense here, it would be a very blurred image.
Hmm.
Okay. So that's
Yeah.
what happens if you make your pinholes big. Basically, you're allowing more light from every point. Okay. And that's opposed to what the ideal situation is. So having bigger pinholes does not solve the problem. And so lenses do solve the problem. Lenses collect more light and also they focus the light at a point. Okay. So both these problems are solved, and that's why we have cameras with lenses. Okay. Yeah. So I think that is what I have written here. So we will, so today and tomorrow, we will talk about how cameras work. Okay. So if we want to have a general understanding of how camera lenses work, we just need to remember again what we learned in physics, some basic ray optics. Okay, so things like light travels in straight lines in homogeneous media. So within the camera, when the light is traveling, or even outside, if your media is homogeneous, then light will travel in straight lines. You don't have to worry about refractions. When a ray is reflected from a surface, then so this image that I have here. Okay, so you have this surface S. When the ray is, first of all, when a ray hits a surface, there are two parts to it, right? That the ray travels through the surface. That's one part of it. That's the refracted ray. And a part of the light is reflected away from the surface, right? So when it's refracted, the direction changes. When this medium changes, okay, the direction of this ray will change. Okay, and for the reflection, since you are going back to the same medium, this angle of reflection does, this angle does not change. Angle of incidence does not change. Okay, and so if in this figure, we have these angles alpha 1 and alpha 2, the angle of refraction. Then if you remember Snell's law, it says n1 sine alpha 1 is n2 sine alpha 2. Okay, where n1 and n2 are the refractive indices of the two mediums that through which the light is passing. Okay, so I'm just sort of revising these things. It's not that we are going to use these heavily in the course, just stuff that you need to remember with respect to how cameras work.